So we have seen so far that if you are looking at prefix-free code and you want to find the minimum length of a prefix-free code for encoding a source x, a random variable x, you must have average length at least entropy of x. And in fact, what we saw was that prefix-free codes, to find prefix-free codes, all you have to do is find code word lengths lx for x in x for each symbol here, such that they satisfy Kraft's inequality, such that summation over x 2 to the power minus lx is less than equal to 1. Okay, so this is, if you recall from the previous lecture, this is Kraft's inequality. So once you find these lengths, we saw in the previous lecture there are two different methods for constructing prefix-free codes. One based on trees and another based on intervals. So all we have to do is find lengths which satisfy this. And of course, while we find these lengths, we keep in mind this benchmark that the best we can do is for the average length is the entropy of x using prefix-free code, of course, and we would try to come close to this hx as close as possible. So recall here that when we were proving this inequality, we saw that equality holds if you can assign the following length, lx equals to log of 1 by px. That was the condition for equality here. However, we can't really choose these lengths because these need not even be integers. These guys are not integers. So what do we do? So here is what Shannon thought. So I'm just calling it Shannon code, which is not really a code, but it's a family of codes. So any code which satisfies the following, a code such that, so it's a condition on code word lengths actually, not so much of a condition on codes. So such that lx equals to log 1 by px, which is the optimal one, but it's not an integer. So we just take a seal of this guy. We'll just call this Shannon code. We'll call any code which satisfies this as a Shannon code. Okay. Okay. So that sounds like a reasonable guess, but is this a valid choice in the sense that do these lengths satisfy Kraft's inequality? So let's check. So the question is, do these lengths lx satisfy Kraft's inequality? Okay, we can just compute the sum and verify. So we want to check if summation over x 2 to the power minus lx, we want to check if it's less than or equal to 1. So this is summation over x 2 to the power minus log 1 by px. Well, but this guy is more than log 1 by px. So you are subtracting more. So if you subtract less, you will only increase the quantity. Right. So here we have just used the fact that the seal is at more than log 1 by px. And so this guy is minus log 1 by px, which is 2 to the power log px, which is just summation over x px, and which is 1. So that's the magic here. So these lengths indeed satisfy Kraft's inequality. Okay. So we can, using the procedure we saw in the previous lecture, and I'll again illustrate it using examples, we can construct a prefix-free code with this length. And we can now check what is the average length of such a code. So we can look at suppose you choose these lengths and construct a code. What is the average length of a Shannon code, the one with these lengths? Yeah, this is just a simple computation. So the average length is summation over x px lx, which is summation over x px log 1 by px. Well, this would be great because this means it would be entropy. So when log 1 by px is integer for all x, then this becomes entropy, which is the best we can do anyway. but it's not an integer, so you have a seal here. But doesn't matter because this guy here is at most log 1 by px plus 1. Okay, so when you expand this sum, split it into two parts, the first term here is exactly equal to this first term here. If you look at this sum here, this is the entropy of x, and then plus 1. Okay, so we can find a code for which you can attain which you can attain hx plus 1. So which implies, so this has an interesting implication, that this L bar, the minimum length of a prefix free code px, we saw that it's more than hx, but we can find a scheme. We just gave a scheme. We just gave lengths, but then using the machinery we developed in the previous lecture, these lengths can be converted to code. They give a code of length hx plus 1, so this can be no more than hx plus 1. Okay, so this guy is between hx and hx plus 1. We nailed it down to 1 bit of accuracy. Okay, so this is great, especially when entropy of x is large. For example, when x is a sequence, so h of xn would grow with n, and the inaccuracy here is just of 1 bit. It's between this and this, and we have a very explicit scheme for doing this. It will give you the lengths, and then we'll use the previous scheme to get this right. So this is the main result we wanted to present in this lecture. Now let's look at some examples to make it more concrete. Actually, I'll just look at one example. So here my source, so alphabet x and probability px, that's what I'll write here. So there are 4 symbols, A, B, C, D, and this one has probability half, this one has probability 1 by 4, 1 by 8, 1 by 8. So I've chosen it in a particular way so that so that log 1 by px is integer for all of them, so we don't need to take a seal. So Shannon lengths for this particular example are given by LA equals to log of 1 by half, which is 2, which is 1, and LB equals to 2. You can check this. LC equals to LD equals to 3. Okay, so you have 2 code words of length 3 and 1 of 1, and of course it satisfies Kraft's inequality. We've already verified this, but in fact this will satisfy Kraft's inequality with equality. Okay, you can check that part. Okay, so these are the Shannon lengths. How do we now convert it into a code? So we had 2 methods for it, a tree based code and an interval based code. How did we do it for the tree based code? So we arrange them in increasing order first and make a tree of the largest length, which is 3 here. So we'll make a binary tree of length 3, of depth 3, sorry. So this is that tree, depth 1, 2, 3. How many nodes are there? 1, 2, 3, 4, 5, 6, 7, 8, right? And we will now choose the first code word, the one corresponding to this guy, LA. And this is the code word of length 1. So I will, maybe I'll label this tree also. So 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. Okay. So LA, I'll put it here. I can choose a tree of length 1. I can choose a node of length at depth 1, and then I remove everything below it. Right. So this guy is gone. So what do we get? So maybe I'll extend this table itself here. So these are my code words associated with different symbols. So this first code word is just 0. And now we can't use any code word starting with 0 because we've removed this tree. Next, we come to the second code word. This is the algo I described in the proof last time, and here is a more concrete realization. So now I'll take the second code word corresponding to, I already have this first code word for 1, and now I'm looking at second code word, let's say corresponding to 2. So I can take a sequence of length 2. So let me take this one here. Okay, so this is the path here that I've taken. First one I've taken this one. So what is the code word here? Code word is 1, 0. So the code word I choose is 10. So yeah, sorry, so it's small discontinuity, but that's fine. We have selected these two code words. The second code word is 10. Uh, but now we have to remove this particular tree which lies below it. So all these guys are also gone, and we have to take two more code words. So the next one we can take, now we need something of length 3, and this tree is not available, this is not available, so only this, and we can only come here. So we come here, sorry, there's a small mistake. Yeah, let me do it again, just 1 second. So this was a tree here, then this one, and we had taken this node here and removed the tree here. Okay, so this was my 10 node, and now I have to select two more nodes, 1 0 1, and both must be at depth 3. So the first node 1 2 3, this one I can select, nothing to remove here, and the second node I can select this one. Okay, so what are the code words? For the first node it's 1 1 0, that's for C, let's say, and then the last one is 1 1 1. Okay, that's this one here. So these are my 4 code words which came out from this method which we saw last time. The first code we just described using a tree. Okay, is this clear? So 0 1 0 1 1 0 1 1 1, and you can check none of them is a prefix of another. Of course, we were removing all the all the possible sequences which are prefixes once we choose a sequence. But we can come up with another code, perhaps another code using a different method, the integer method that we saw. So let's repeat a similar procedure using the interval method. So we start with 0. We start with the number 0, and the first interval that we associate with this a is, it starts with 0.0, and it's an interval of length 2 to the power minus 1, so of half. So this one ends at this point. Okay, maybe it's better to draw this here. Okay, so this interval, this guy here, is associated with the first code word. Okay. And we can just use the sequence 0 of length 1 as the code word. Okay, so we can do that. So this is just the same as this one, 0. Now next we look at this IB, which starts here at 0.1, and now we are looking for an interval of length 2 to the power minus 2, which is 0.01. So it just goes to 0.1 plus 0.01, so it's 0.11. Okay, 1/4. It's this plus 1/4. So it starts here, ends here. This is the next. This is the interval corresponding to the next code word. So we can just mark it here. And what is the code word? Well, we have to take a code word of length 2, so it's 1 0. Remember, you can just view it as 1 0. And here it is 0 0. Yeah. Next, again this is IC. It starts. So yeah, this one is also the same 1 0. In fact, in this case, what we will end up seeing is that it has the same code word, the same code words as before, but the method is different. So you start here now, and you end at. So you start here. What is the starting point? It's 0.11. But I will take a sequence of length 3, so I'll put a 0 here. So this is this same code word again, and now you have to add to it 2 to the power minus 3, which gives you this. This is all in binary, by the way. This is all in binary. So this guy ends here, and that's your third interval. Which yeah, what is the color we're using? Yellow color. Yeah, the same. We can see this one also still looks the same. And again, the final one, ID, starts at 0.111 and goes all the way to 0.111 plus 2 to the power minus 3, which you will see gets you here. Okay, starts here, gets you here. This is the final interval. So these are the 4 intervals, which get associated with these different code words, and yeah, this sequence again. So is 111. So this is the second construction. In this case, it turns out that both gave us the same answer. In fact, that's because of the fact that these were powers of 2. But it's not an important point. There were 2 different methods. Through this example, I wanted to illustrate these 2 different methods. Okay. And we had given you a guarantee that this code word, the final code that comes out, which has these Shannon lengths, will be within 1 bit of entropy. But in fact, in this case, the distribution, all the probabilities were powers of 2, and therefore all these log of 1 by px were integers. We didn't have to take the seal. So we must have that the average length is equal to entropy. Let's just verify it. So what is the average length of this code? Average length is half into 1 plus 1/4 into 2 plus 1/8 into 3 plus 1/8 into 3. Right, that's the average length. But all these numbers here are corresponding to log of 1 by px. So this guy actually will turn out to be equal to its entropy. You can compute the entropy. And the number, if you want a number to it, is half plus half 1 and 3 by 4. So it's 1 plus 3 by 4, which is what? 7 by 4. Okay, that's the average length, which is equal to the entropy. Okay, so this concludes this lecture. What we saw is that Shannon lengths can be used to get a prefix-free code with average length less than or equal to hx plus 1. And once you get those lengths, once you get Shannon lengths, you can either use the tree-based representation or interval-based representation to construct your code. Both algorithms will work, and I gave an example to show how those algorithms work. Okay, this is all I wanted to say in this class. See you in the next lecture.